I'm reading from The Greatest Lie on Earth, Proof That Our World is Not a Moving Globe by Edward Hendry. Chapter 5. Airplane Level Flight Proves the Earth is Flat. If the Earth were a globe, airliners would not be able to fly on a flat and level path. Any pilot will tell you that once a plane gets to its cruising altitude, the pilot, quote, levels off, close quote, and flies in a straight and level path. Indeed, the pilot uses the horizon to ensure that the plane is flying level. When visibility is poor, the pilot will use the instruments and fly a level heading using an artificial horizon. Either way, at all times, the plane flies level once the pilot reaches cruising altitude. If the Earth were a globe, the pilot would have to constantly adjust the heading of the plane and dip its nose down to keep a constant altitude. However, the Earth is in fact flat, so if a pilot dipped the nose of the plane down to adjust for the supposed curvature of the Earth, he would find that he is losing altitude. If the pilot kept on that downward trajectory, the plane would crash into the Earth. The fact that no such downward adjustment is made by pilots for the supposed curvature of the Earth is proof that the Earth is flat. Eric Dubay explains, if the Earth were a sphere, airplane pilots would have to constantly correct their altitudes downward so as to not fly straight off into, quote, outer space, close quote. If the Earth were truly a sphere, 25,000 miles circumference, curvating 8 inches per mile squared, a pilot wishing to simply maintain their altitude at a typical cruising speed of 500 miles per hour would have to constantly dip their nose downwards and descend 2,777 feet, over half a mile every minute. Otherwise, without compensation, in 1 hour's time, the pilot would find themselves 166,666 feet, that's 31.5 miles, higher than expected. A plane flying at a typical 35,000 feet, wishing to maintain that altitude at the upper rim of the so-called troposphere, in 1 hour would find themselves over 200,000 feet high into the mesosphere with a steadily raising trajectory the longer they go. I have talked to several pilots, and no such compensation for the Earth's supposed curvature is ever made. When pilots set an altitude, their artificial horizon gauge remains level, and so does their course. Nothing like the necessary 2,777 foot per minute declination is ever taken into consideration. Indeed, the Federal Aviation Administration FAA assumes a flat Earth when training pilots and air traffic controllers using their Target Generation Facility, TGF. The TGF consists of several software programs that control simulation scenarios using simulated aircraft. The TGF computer simulator drives almost all of the air traffic control laboratories at the FAA William J. Hughes Technical Center. The FAA states, quote, "Our lab has worked closely with the TGF group to have aircraft perform the way air traffic controllers would expect them to behave in the real National Aerospace System, NAS. The simulated aircraft in TGF are quite realistic representations of their real-life counterparts." Close quote. The software used in the TGF must be accurate in order to properly train pilots and air traffic controllers on the behavior of aircraft in flight. The assumption of a flat Earth can be seen in a publication from the FAA. The Engineering, Analysis, and Design of the Aircraft Dynamics Model for the FAA Target Generation Facility, TGF. That FAA publication explains the software that is used by the TGF to accurately simulate the behavior of aircraft over the Earth. Specifically, this document discusses the detailed engineering, design, and software implementation of an aircraft dynamics model, ADM, suitable for incorporation into the FAA TGF simulations at the FAA William J. Hughes Technical Center, Atlantic City, New Jersey. The model is designed to be implemented on computers located within the facility and to work in conjunction with software models of radar, data links, and other air traffic management ATM equipment to provide real-time simulation of aircraft operating within the National Aerospace System, NAS. The FAA publication explains that in order for the software to accurately replicate the behavior of aircraft during flight over the Earth, the software running the TGF simulator assumes that the Earth is flat. The observant reader will notice that the aircraft equations of motion were calculated assuming a flat Earth, and that we here assume the development frame was the northeast down frame. This implies necessarily that the Earth rotation and the variation of the gravity vector with position over the Earth were ignored in developing the aircraft equations of motion. This simplification limits our mathematical model to the flight of aircraft only. The model will not properly handle the flight of suborbital craft and spacecraft such as intercontinental ballistic missiles, satellites, or the space shuttle. The model is adequate for all vehicles traveling under Mach 3. Notice that the FAA document both assumes a flat Earth and ignores the rotation of the Earth and gravity. The FAA maintains that the computer model assumes a stationary flat Earth and at the same time remains precise and accurate regarding the flight of aircraft. The only way that a stationary flat Earth can be the basis for a model, and that model still be accurate, is if the Earth is in fact flat and stationary. That means that the ignored gravity and rotating globular Earth do not affect the accuracy of the model because they do not, in fact, exist in reality. The proviso in the last sentence that the computer model does not address spacecraft or satellites is meaningless surplusage. The statement that the model is adequate for all vehicles traveling under Mach 3 is also meaningless, since it does not specify that it would be inaccurate for vehicles traveling over Mach 3. The entire purpose of the TGF simulation is to create as real a simulation of actual aircraft flight over the Earth as is possible. The only way to do that is to simulate what is real. That is why the TGF software assumes a flat Earth. The TGF is designed to have, quote, high fidelity, close quote, to reality. The FAA publication states, currently, the aircraft dynamics incorporated in the TGF are based on the first principles of physics and aeronautics. The models provide the performance characteristics needed to support high-fidelity simulations. The TGF incorporates fuel burn models, environmental, weather effects. Additionally, the modeled aircraft are representative of commercial air traffic in the U.S. national airspace, NAS. As future simulations are developed or brought to the technical center, higher fidelity will be required to identify NAS operational safety and performance issues. The TGF is prepared to increase its fidelity and operational connectivity required to meet the demands by other FAA programs and simulators. The goal of this project has been to develop and maintain a high-fidelity simulation capability to meet the needs of the FAA in operating, testing, and evaluating its NAS. The reality to which the TGF software is faithful is that the Earth is stationary and flat. If the TGF simulator based its model on the false premise of a globular, spinning Earth, it would create a safety issue for aircraft. The FAA simply had to assume a flat Earth because that is reality. If the FAA had assumed a spinning, spherical Earth model, the pilots and air traffic controllers would be trained improperly and create the messy and embarrassing result of planes crashing with regularity. Indeed, since safety is paramount, it was necessary for the FAA to verify with real-life testing the algorithms in the TGA simulator that assume a flat, stationary Earth. The FAA publication states that, quote, "The document concludes with a section on verification and validation, the process by which the various features of the simulation are tested and verified," close quote. What did the section on verification reveal? The FAA publication reports that, quote, "The testing that was done to verify and validate the TGF simulation gives us a high degree of confidence that the models contained herein have sufficient fidelity for their use as a target generating tool." The models that the testing validated as being faithful to reality to a high degree of confidence assumed a flat, stationary Earth. That means that the FAA verified through actual testing with aircraft with a high degree of confidence that the Earth is flat and stationary. The U.S. government implicitly acknowledged the reality of the flat, stationary Earth in another official publication. In NASA's 1988 publication, number 1207, titled "Derivation and Definition of a Linear Aircraft Model," it states that the generally accepted linear aircraft model is based upon, quote, "a rigid aircraft of constant mass flying over a flat, non-rotating Earth," close quote. Every commercial and military aircraft has on board an instrument that can only work on a flat Earth. That instrument is the attitude indicator, which is also known as an artificial horizon. That artificial horizon instrument has a display that shows the pilot the attitude of the plane to the active horizon, even if he cannot see the horizon because it is obscured by inclement weather or darkness. The pilot can determine the roll of the aircraft, i.e., if he is flying level, and the pitch of the aircraft, i.e., if the nose of the aircraft is pointed below or above the horizon. That attitude indicator works by means of a spinning gyroscope mounted on a gimbal. A gyroscope has two important properties: 1, rigidity in space, and 2, precession. All practical applications of gyroscopes are based on these two properties. Precession means that the gyro will resist any force that attempts to change its plane of rotation. A force applied to the gyro will result in a movement of the gyro, but not in the direction of the applied force. The gyro will instead move at right angles to the direction of the applied force. The rate of precession is in direct proportion to the applied force. The most important property of a gyroscope for a pilot is rigidity in space. That means that the gyroscope will retain its horizontal attitude parallel to the direction of the spin of its rotor and retain its vertical attitude in relation to its rotor's axis. The rotor's axis around which it spins is the y-axis, vertical. The horizontal plane of the rotor is on the x, lateral axis, and the z, depth axis. Thus, if the spinning gyroscope is on a gimbal that allows for rotation along three axes, x, y, and z, the gyroscope will retain its original attitude in relation to the x, y, z axes, and the gimbal will move around the fixed gyroscope. The x, y, z axes of the gyroscope will remain rigid in space, offering a fixed matrix upon which the airplane can move. Any difference between the fixed axes of the gyroscope and the moving airplane will show up in the coordinates on the attitude indicator instrument. That is what the gimbal attached to the aircraft in the instrument bay allows, as illustrated in the following frames from a U.S. Navy training film produced in the 1960s explaining how gyroscopic flight instruments work. The spinning gyroscope in the attitude indicator stays fixed and rigid in space. The gimbal in the attitude indicator instrument allows for the aircraft to move in relation to the fixed axes, x, y, and z, of the spinning gyroscope. Thus, the pilot can see, by looking at the attitude indicator instrument, the exact attitude of his plane in relation to the horizon. The problem with the spherical Earth model is that a plane with an attitude indicator showing straight and level flight will cause the plane to fly off into the upper atmosphere as the curve of the globe falls away from the aircraft. The only way that a pilot on an aircraft can fly a straight and level path using his attitude indicator is on a flat Earth. Below is a frame from a United States Navy training film, circa 1960. The frame illustrates the inherent impossibility of maintaining level flight for an aircraft using gyroscopic instruments on a spherical Earth. The gyroscope depicted in the frame is seen to maintain its rigidity in space as it hypothetically circumnavigates the globe. As is obvious by the rigid attitude of the gyroscope, a plane with a gyroscopic attitude indicator would be gradually heading out toward the upper atmosphere as it traversed the globe. Indeed, as indicated in the film illustration, the plane would be in a vertical trajectory after flying 1/4 of the circumference of the Earth, a distance of approximately 6,250 miles. Incidentally, the training film narrator tried to explain away this apparent problem by stating that there is a continuous adjustment to the attitude of the gyroscope built into the attitude indicator instrument. However, the mythical, on-the-fly adjustment to the gyroscope is impossible, as such an adjustment would render the gyroscope useless. Recall that the fundamental property of a gyroscope is that it maintains its rigidity in space. If the fundamental property of a gyroscope, rigidity, can be so easily altered, that means that rigidity is not truly a fundamental property of a gyroscope. An adjustment to the fundamental characteristic of rigidity in space of the gyroscope, if it were possible, would defeat the whole reason to use the gyroscope. It would make no sense to use an instrument with a gimbaled gyroscope that would require an additional feature to neutralize the primary property of the gyroscope, rigidity. The supposed neutralizing feature of the instrument would need to detect the precise curvature of the supposedly ball Earth and maintain a true course over its surface. If it could do all of that, why add the complication of a gimbaled gyroscope? An attitude indicator with gimbaled gyroscope would only be a hindrance on a ball Earth. Rigidity in space is exactly the opposite of what is called for in an attitude indicator on a spherical Earth. A gyroscopic attitude indicator instrument is necessary on a flat Earth, but that same instrument would be pointless and even dangerous on a spherical Earth. A gyroscopic attitude indicator keeps its attitude precisely perpendicular on its axis, on a fixed plane to the spin of its rotor, and perfectly level in relation to the surface of the Earth, because the Earth is flat. The rigidity in space of a moving gyroscope that maintains its attitude is only useful in an attitude indicator on a flat Earth. A gyroscopic attitude indicator simply will not work on a globe. One interesting thing revealed in the above illustration from the United States Navy training film is the fact that if the Earth were a spinning globe, a gyroscope in a gimbal placed on a level table would show the spin of the Earth if the Earth were spinning. Thus, if the Earth were spinning, the gimbal surrounding the gyroscope would show a movement of 1.25 degrees within 5 minutes and 15 degrees in 1 hour. As the United States Navy training film illustrates, after 6 hours, the gimbal should turn 90 degrees underneath the gyroscope on a spinning globe. Such an experiment using a gimbaled gyroscope has been performed. The experiment showed no movement whatsoever of the gimbal around the gyroscope, thus proving that the Earth is not a spinning globe.
There's still energy left in this flywheel though, so let's give it a little push.
Okay, so we saw how by letting it come to a complete stop before spinning it up, it would appear not to show any apparent drift whatsoever in either direction. I've done it countless times now. I've got lots of different experiments on video in all different scenarios. I did it lots and lots of times. and not once did I see anything that resembles apparent drift either in speed or direction.